Okay, so this is the first lesson in chemical kinetics, the study of rate of reaction. All right, so today we're going to talk about average rate of reaction, instantaneous rate of reaction, and what factors can affect the rate of reaction. So in this section called chemical kinetics, this is the area of chemistry where we get involved with rates of reaction. How fast does reaction occur? And the reaction rate is just a way of saying a change in the concentration of the reaction or product per unit time. Okay, change in the concentration of reaction product over change in time. Some reactions are very fast. Like, for example, if you want to do a combustion reaction, a burning usually occurs very fast, like combustion of propane. It's so fast that we consider that to be like an explosion. So it happens within a fraction of a second. Other reactions, like this one, the oxidation of silver, takes literal years. If you buy new silverware, it's all shiny and lustrous, but then after like a few decades, it loses its luster. It's kind of dull. Well, that's because the silver is slowly oxidizing. It's not obvious. You're not going to just wake up the next day, hey, my new silverware rusted. No, that's not going to happen. But this does take a long time. All right, so this is a slow reaction. Reaction comes in all kinds of different rates. Some are instant, some are just years. And really, we don't know how fast the reaction is until we actually investigate it. The math, just by looking at the balanced equation, the thermodynamics, it doesn't actually tell us how fast the reaction will occur. Okay, thermodynamics, the thing we just learned, it gives us information about the energy transfer, but not about how fast this occurs. So if you want to determine the rate, it's like determining the speed of a journey. Okay, if you want to know speed, then you need to know two things. A, how far did you travel, the distance traveled? And B, how long did it take you to get there? So time. We all know in physics, speed is distance divided by time. All right. Same thing with rate. Reaction rate is just the speed of the reaction. This is kind of like distance divided by time. Instead of tracking distance, we track the appearance of a product or the disappearance of a reactant. They're equally good at particular time points. Okay, just like measuring speed. There are many ways of doing this. Which method do we use depends on the reaction itself. Some of these methods include tracking the gas volume if you produce a gas, tracking the color or the mass of the reactant or product, or the pH if it produces acid or base, or electrical conductivity of your solution if you produce or consume ions. Let's look at some of these examples. Now, if you want to measure the rate of a reaction, you don't want to disturb the reaction. Your observation should not affect the reaction in any way, otherwise you have inaccurate results. So the best ones are just to measure the production of a gas. If you're just measuring the gas produced, you're not really disturbing the reaction. Or you can just measure the amount of ions or the color change. So what type of reaction are you able to measure the production of a gas? Well, your reaction must produce a gas. And that is the only gas. You don't have gas in the reactants. You don't have gas in the product except that one. So the gas produced must be that gas. Like, for example, here, HCl and zinc, if you drop zinc into hydrochloric acid, it will start to bubble and produce hydrogen. And if you can harness that gas, like, for example, with a test tube and water over there, you can just measure the volume of that gas, how fast that volume is changing. You can then deduce the rate of this reaction using numerical numbers. All right. So you must produce a gas in order to use this method. The next one is with ions. Which reaction can we just measure the ions? Well, one that produces ions. If your products have more ions in your reactant or less ions than your reactant, my point is they're not the same, then you can measure the rate of change of ions using electrical conductivity. The more ions you have, the better you are as a conductor. All right, so if you just hooked up that apparatus right there with the solution and you have a reaction in there, you can just look at the brightness of the light bulb. You can measure the luminosity of the bulb and how fast it changes based on, you know, the concentration of the ion you have in the solution. The higher the ion concentration, the brighter the bulb should glow. So this method can work if you produce ions. Now, if you produce an acid, you can measure the pH. All right, so for example here, if you put sulfur trioxide into water, it will dissolve into sulfuric acid. And the presence of an acid will lower the pH, so you can just measure the change of the pH. The faster the pH changes, the faster the rate of reaction. All right, and of course, you can do the same thing with the base. If you produce a base, well, the pH will still tell you. And you can measure mass. Now, this one is not really recommended because it's really difficult to measure the mass, but here's one example. If you have an open system where a gas is freely able to escape, and your product, one of them is a gas, then you can just measure the change in the mass. You see what I mean? Because of conservation of mass, the mass of the product should equal to the reactant. But if the gas escapes, then you should have a smaller mass. And how fast do you change the mass just tells you how fast the reaction occurs. And so that is one way to measure the mass. Now, usually this sucks because if you want to measure the mass, you're probably going to mess up the reaction. You're going to have to manipulate the reaction a little bit, and that's not nice. This one is just dumb. You might as well just measure the gas, right? Okay, last one is color change. If you have a reaction that has different colors for the reactants and products, you can just measure the color change. Right? But this only works if your reactants and products have different colors. You can measure the rate of change of an appearance of or disappearance of a color, and then that will tell you numerically what is the rate of reaction. Okay, so which method we use depends on the reaction itself. Okay, you cannot apply anything to any reaction. So for example, the one on screen right now, you can't measure a gas because you don't produce a gas. You see what I mean? So just make sure that you use your common sense to determine how you can measure the rate of reaction. Now, let's talk about the mathematical portion of this. Reaction rate, we use the letter R to represent reaction rate, which makes sense because it starts with R. This is expressed as change in concentration of either reaction or product, doesn't matter, delta C, okay? Concentration is measured in moles per liter, and delta, the change in concentration, is still moles per liter, divided by time, delta T, the change in time, the unit is. So that'd be T final minus T initial. So if you have concentration, which is moles per liter, divide by time, which is second, the unit for reaction rate should be moles per liter per second. Does that make sense? Now, this might look very familiar to you guys because you just learned calculus and vectors. And you talked all about rate of change in calculus. Right, and this delta C over delta T, this is just the average rate of change over a time interval. If you have two time points, you want to find the rate of change on average between them, well, that's the formula you need, delta C over delta T. Graphically, if you have a curve that represents a rate of reaction, you want to measure the average rate of reaction between 2 points. Well, in calculus, you learned that that is just the slope of the secant between those 2 points. And to calculate the slope, it is rise over run. So if you look at this chemistry example, on the x-axis you have time, so how long the reaction elapsed, and on the y-axis you have concentration. So you start with a high concentration and that gradually decreases as it is being consumed. And if you want to measure the average rate of change between, let's say, 20 seconds and 100 seconds, well, just plot the 2 points there on the graph, draw a straight line, that's called the secant. The rise would be the change in concentration, and the run would be the change in times. So basically, it is the same as the formula, delta C over delta T. All right, so does that make sense? Obviously, calculus is not a prerequisite for this course. I cannot assume that you know how to do calculus because some people don't take calculus, just chemistry, or some people take chemistry before calculus. So I am not expecting you to perform crazy math here. It's just a really basic math, draw a line, rise over run. That's basically the extent that you need to know. Nothing fancy. You don't need to use like the first principle or something crazy like that. So let's look at example 1. Measurements taken during the following reaction show the concentration of carbon monoxide, CO, of 0.019 moles per liter at 27 minutes and 0.013 moles per liter at 45 minutes. Calculate the average rate of loss of carbon dioxide, so carbon monoxide, and the gain of carbon dioxide. All right, so you're converting CO into CO2. You're losing CO, but you're gaining CO2. And this tells you at 2 specific time intervals what the concentration of CO is. Very, very simple problem. Use the formula delta C over delta T. The change in concentration of carbon monoxide divided by the time interval. The only thing you need to take note of is you have to use seconds for time, not minutes. The SI units of science for time is always second. Excuse me. So plug in the numbers. The final concentration at 45 minutes is 0.013. Okay, that's the final minus the initial 0.019. That's delta C. The time being delta T, well, it just happens that at 45 minutes you have 2,700 seconds, and at 27 minutes you have 1620 seconds. Just subtract that. You put this in your calculator, you take the positive value, whatever it becomes. You have 5.6 times 10 to the negative 6 moles per liter per second. All right, so that is the rate of disappearance of carbon monoxide. All right, so do you guys have any questions? All right, cool. So this is quite straightforward. Then you can calculate carbon dioxide. Now, I didn't provide you with the chemical equation, probably because I forgot to put it in, but here it is. CO plus NO2, you become CO2 plus NO. So you know that carbon monoxide disappears at this particular rate. And if you look at the balanced equation, for every 1 mole of CO, you have 1 mole of CO2. It's a 1-to-1 ratio. Meaning that if you lose CO at a particular rate, you will gain CO2 at the exact same rate. So to calculate this, despite not having any information on CO2, you can still calculate using CO. All you have to do is convert into CO2 using the mole ratio. All right, what do we mean by the mole ratio? It's a 1-to-1 ratio. Just compare the coefficients in the balanced equation. For every 1 mole of CO2, you consume 1 mole of CO. So if you just multiply this, I shouldn't have the second line. Those two values would cancel, and you will have moles of CO2 per liter per second. Okay, now this doesn't change the answer mathematically because you're multiplying by 1, but it's still important. We're doing science, we're not doing math. Okay, we are converting the units. The same number, yes, but different units mean very different things. 1 cup of acid versus 1 cup of orange juice, that's very different. Actually, bad example, orange juice is acid. 1 cup of acid versus 1 cup of base, very different. All right, so please, the units matter. You need to convert to the correct unit by performing a calculation. You can't just assume that they're the same. All right, so if you multiply by 1, obviously the number wouldn't change. So there you go. It's the same number, 5.6 times 10 to the negative 6 moles of CO2 per liter per second. So you can conclude that the rate of decomposition of CO and the rate of formation of CO2 are exactly identical, same number. Any questions? All right, so this one is supposed to be fairly simple. It's a very simple calculation. Apply the formula, boom, you're done. All right, this is 3 marks even in math class. So here is instantaneous rate of change. Instantaneous rate of change is the rate of reaction at a particular time during the reaction, at one particular time. average rate of change is between 2 time periods, so it's an interval. But this one is 1 moment. And how to determine instantaneous rate of reaction? Well, if you just draw a dot at that time period, and you manage to draw a tangent to your curve, you can calculate the slope of that tangent. And that will give you the instantaneous rate of change. So another review of math class, IROC, instantaneous rate of change, is the slope of the tangent. Okay, AROC, average rate of change, is the slope of the secant. So math is useful, that comes back. Obviously, we are not going to do any calculus in chemistry class. All right, you do not need to take the derivative, you don't need to use the first principle. Here's the stupid way. If you see a question, I give you a graph and I ask you, so what is the instantaneous rate of change at, I don't know, 20 seconds? Cool, you take a ruler, very carefully, you position the ruler so that, that looks like a tangent. You draw a line and you measure the slope. You measure the rise, you measure the run, and then you do the math. That's what you would do. Okay, that is, I understand that's dumb. Why would you estimate when you can just use math to solve? Well, because I can't assume that you know the math. Very often when I teach math in the earlier grades, we learn some concepts that can be easily solved with a higher level math. But because the students are not there yet, you have to use a long and tedious method. I really hate those type of questions. Sometimes I just teach them the better method, so that they wouldn't have to use the stupid method. A classic example is in grade 11. You learn about exponents, and you have to solve for an exponent, but you never learn how to do that. So the textbook actually tells you to take a calculator and guess and check. I'm like, what? I just taught them log in grade 11. They don't have to use it. If they want to guess a check, by all means, but if you want to do it the smart way, use log. Here, the best way is calculus, but you can't do that. You can't assume that you know that. I'm not going to teach you that in this class. So I'm not going to put stupid questions like this on the test. I'm not going to draw a curve and hey, what's the instantaneous rate of change? You're all going to give me different answers because you're all going to eyeball with a different ruler, with a different angle. So all you have to know is instantaneous rate of change is the slope of the tangent, rise over run at that point. That's it. Okay. But the questions like this are fair game. I can ask you to compare the instantaneous rate of change. So if you look at this graph, you have concentration versus time for nitrogen dioxide gas. Determine whether the rate of appearance of nitric monoxide gas, I think that's a spelling mistake, is fastest at 100, 200, or 350 seconds. The tangent lines to the curve of nitrogen monoxide gas at these points are shown in pink. Okay, if you look at the pink tangents, those are the ones I want you to compare. So which one would have the fastest rate of change? Just tell me. 100, 200, 350. Oops. Guys, you guys are there? 100? Well, yeah, this is a no-brainer. Okay, I'm surprised it took that long for an answer. All we have to do is look at the steepness of the slope. The steeper, the more slanted the slope is, the higher the rate of change, and the more flattened the slope, the slower the rate of change. And because the graph is slowing down, the earliest one at 100 is the steepest slope, at 350 is almost 0. So all you have to do is just compare the slopes, and you realize at t equals 100, you have the largest slope, thus fastest instantaneous rate of reaction. Okay, so is that clear? All right, so example 3, it gives you one instantaneous rate and asks you to calculate the instantaneous rate for another compound. So you don't need calculus for this. All you have to do is use stoichiometry. if the rate of consumption of N2O5 at a certain instance is 5.6 times 10 to the negative 2 moles per liter second, determine the rate of appearance of oxygen at the same time. And so you know the rate of disappearance of N2O5. What is the rate of appearance of oxygen? How would you do something like that? You know the rate of disappearance, that's given to you. Okay, just copy that down. So just think about this logically here. For every 2 moles of N2O5 consumed, you would synthesize 1 mole of oxygen. All right, so the rate of appearance of oxygen is half of the rate of disappearance. So this basically tells you divide by 2, which is exactly what you do. But if you want to do this properly, showing all of your steps, you can use stoichiometry, the mole ratio between N2O5 and O2. Okay, for every 1 mole of O2, you have 2 moles of N2O5. So if you multiply by 1 over 2, you cancel out the moles of N2O5. So your final answer should have 1 mole of O2 over liter second. That's your unit. Well, all you have to do is really just divide by 2. So you would have 2.8 times 10 to the negative 2 moles per liter per second. All right. Do we have any questions about how to calculate instantaneous and average rate of change? All right. So these are probably going to be just like simple, even multiple choice questions because, you know, there's not even that many steps to solving these problems. All right. So which brings us to the next part. What factors affect the rate of a reaction? All right, and there are 5 different factors that affect the rate of a reaction. I don't ever recall teaching this earlier in an earlier grade, so I'm assuming that this is the first time you're going to hear about this. But I just wanted to see how many of you actually know this. Can somebody name some of the ways that reaction rate can be affected? People?
Temperature?
I'm gonna guess heat.
Yeah, heat, temperature. Yep, that's definitely one. And?
Presence of a
Condensation.
Oh, yeah, I heard catalyst. What was that?
Condensation.
Well, concentration. That makes sense.
Yeah.
And? Half of you came from bio. Come on now. You remember Unit 1? You learned something in Unit 1 in biology, biochemistry. Something that changes the rate of reaction.
A catalyst?
Yes, a catalyst or enzymes in biology. So those are 3 pretty obvious ones, but there's 5. And we're going to go through the 5, what they do to the rate of reaction. And tomorrow's class, we're going to learn why they have that effect. The first one is the chemical nature of the reaction. Nobody mentioned this one. Some things just naturally react faster than other things. It has to do with their structure, with their electronegativity, with their tendency to lose or gain electrons. And you know they're different across this periodic table. Somebody said concentrations. That's a good one. Differences in concentration do matter when it comes to rate of reaction. And then temperature, that was the first one said. Presence of a catalyst in living things and enzymes. The last one is surface area. Nobody mentioned that one, but a surface area would also have a significant effect. So I'm going to introduce each one of these and tell you what exactly they do to the concentration, to the rate of reaction. So the first thing, chemical nature. Certain elements, especially alkali metals, they have high tendencies to react, and the transition metals, mostly, they have low tendencies to react. Sodium is so reactive, alkali metals in general, not just sodium, the entire column. They're so reactive, they react with the air. you can't just expose them in the air like that. They will react and disappear because there's water vapor in the air and they react violently with water. And if you touch them, it will react with your hand because your hand usually has sweat. Okay, so I would not touch these metals with skin. Silver and gold, on the other hand, they're really unreactive. They're so unreactive, we have actually used them as currency throughout history, even today. Right? If you're filthy rich and you don't trust the dollar, you buy gold. You store it in a bank vault. If gold was reactive, okay, you go back a year later, hey, where's half of my gold? Well, it reacted with the air. That would be a terrible, terrible thing. So we don't use sodium as currency for good reasons. You can't just hand over sodium because you burn your hand. Gold and silver, they're unreactive, so they can basically last for decades without changing its mass. All right, it's very difficult to get gold and silver to react. Silver less so, but especially gold is really hard to get gold to react to something. So as a result, we use that property to our advantage. All right, so differences in their chemical nature can account for differences in rate of reaction. So sodium will probably always react faster than gold. Doesn't matter what you do, sodium is going to be faster. Next, concentration. The higher the concentration, the faster the rate of reaction. You may have an idea of why this is the case, but tomorrow we'll focus on exactly why. But if you look at this graph, on the x-axis, you have concentration of hydrochloric acid. So as the concentration increases, on the y-axis, you have duration of the reaction. The shorter the duration, so the faster it is to complete. Higher concentration equates to faster rate, all right, which means shorter time. Surface area, it might not be obvious at first, but if you think about the geometric shape of various compounds, if you have a cube, all right, a cube would have a certain volume and you could calculate the surface area. But if you slice the cube up into little pieces, little cubes, you will still have the same volume, but you have drastically increased surface area. And in order for chemical reactions to occur, you need a surface area for this to occur on. So the greater the surface area, the faster the rate of reaction. All right, so this is the reason why your intestines have a great surface. You have villi and microvilli to increase the surface area so you can digest food more efficiently. Right? This is illustrated in cooking as well. If you just try to grill a steak, you put the steak in, you flip it over after a few minutes, and then you cut it open to eat, and you can still see the blood inside. It is medium rare because the heat only really got to the surface. You don't have a large surface area. If you cook steak in the Japanese style, teriyaki, you chop it into little cubes, and then you grill that. That will quickly cook because little cubes have drastically higher surface area, right? And if you're a kid, I remember in grade 5, my teacher made us do an experiment. We all got a cube of ice, and she asked us to melt that ice. You can't put it in your mouth, but you can do whatever else you want. So I just held it in my hand, used my hand temperature. Didn't work out, and it took a long time. And then the teacher told us, well, if you broke the ice, because of the increase in surface area, you will melt it faster. At the time, I was like, huh, really? Well, the more you know. So now that I know more about chemistry, I was like, oh yeah, that makes sense. She was trying to tell us about surface area. So increased surface area means faster reaction rate, all right? Okay, temperature. If you increase the temperature, you have a faster reaction rate. And in fact, empirical evidence suggests that if you increase the temperature by 10 degrees Celsius, the rate of reaction for many reactions will double. And the reverse is true. If you decrease the temperature by 10 degrees, the rate of reaction will halve. And this chart illustrates the effect of temperature. So you have time of reaction on the x-axis, volume of a gas produced. As you can see, there are two curves. In the blue, you have a higher temperature, 100 degrees. And you can see that the volume increases way faster compared to the 75 degrees, right? Because increased temperature increases the rate of reaction. This explains cold-blooded animals, why they want to seek sunlight. So these poikilotherms, their body temperature depends on the external environment. So they have to regulate the temperature by going into the sun. So at night, when there is no sun, they usually remain dormant and inactive because they have a slowed metabolism from the lack of temperature. And during the day, when the sun comes out, they go into the sun, they heat up their body so that their metabolism will increase, which enables them to walk around, digest food, whatever. All right, so that's the effect of temperature on the rate of reaction. And the last one, a catalyst is something that increases the rate of reaction, but it is not consumed. All right, so after the reaction, it is still there. You can use it again and again and again. So in biological systems, we also have catalysts. It's just that they're made up of proteins, and we call them enzymes. They do the exact same thing. They speed up chemical reactions. Without enzymes, we will just drop dead in like a second or less than that. Enzymes are constantly keeping you alive by, making sure that your body's metabolism is working. Every single reaction in your body needs an enzyme, and without it, it just doesn't work. So an enzyme will basically force a reaction to happen. Normally, without the enzyme, the probability of that happening is too low. And two molecules, they want to combine together, but if you're just bumping around, it's really rare for them to bump into each other and just happen to react. But an enzyme would just grab both, boom, put them together because they already have the proximity and the orientation. So all they have to do is just change the shape a little bit and they will react. So this will drastically increase the rate of reaction. A reaction that normally takes years would occur in a fraction of a second. Okay, so that's the effect of a catalyst. The key thing is a catalyst is not part of the reaction. It is not consumed. It will stay behind and catalyze a new reaction once it's finished. All right, so this is it for the lesson on reaction rates. We learned about average rate of reaction, instantaneous rate of reaction, how to measure rate of reaction, and finally, the big five, the 5 factors that affect rate of reaction. So for next class, we're going to learn why they affect rates of reaction. Right, today we learned how they affect rate of reaction, mostly increase, the thing we talked about, but why do they increase? What is the mechanism behind the logic here? Why does it increase instead of decrease, or why does it have an effect at all? So do we have any questions?
Are we going to have an assignment for this unit?
Yeah, about that. Let me just turn off the camera.